Imagine two tiny particles created together. They stay connected somehow, no matter how far apart they get.
Miles, light years, it doesn't matter.
And if you measure something about one, you instantly know something about the other. Instantly. It really makes you pause, doesn't it? Challenges our everyday thinking.
It certainly does. It's one of the deepest mysteries, or perhaps features, of quantum mechanics.
So today we're doing a deep dive into this, into quantum entanglement. We want to focus on, well, the core physics. How do these seemingly impossible connections actually happen?
We'll look at why properties like spin are correlated and, why the particles often fly off in opposite directions.
And we'll also get into the history, that whole debate it kicked off, and how experiments finally proved this strange reality.
Our discussion draws from a set of sources called Entanglement, the inseparable bond of quantum systems, looking at first principles and really deconstructing quantum spin.
It feels like a journey from a weird idea to solid experimental fact.
Driven by some really fundamental principles of how the universe works.
Okay, so to really get how this spooky action works, we need to tackle quantum spin first. It's key, right? But what is it? The name sounds off.
It really is a bit misleading, that name spin.
Yeah.
It's purely historical. It's definitely not literal rotation, like a tiny ball spinning.
I don't know. It seems intuitive.
Well, if you tried to make something as small as an electron physically spin fast enough to account for its properties, parts of it would have to break the speed of light.
Right. Violating special relativity, big no-no.
Exactly.
Yeah.
Wolfgang Pauli, one of the pioneers, he called it a classically non-describable two-valuedness.
Catchy.
Well, maybe not. But what he meant was spin is a fundamental, intrinsic kind of angular momentum.
Intrinsic.
Yeah, think of it like electric charge or mass. It's just a property a particle has. It doesn't arise from motion. It's just there. And there's no real macroscopic equivalent, nothing you can point to in our everyday world and say, it's like that.
So it's just a fundamental quantum property. And I gather it's quantized, meaning it only comes in specific amounts.
Precisely. It takes on discrete values. Every fundamental particle type has a fixed spin quantum number, S. For every single electron out there, for instance, S equals 1/2.
Okay, S12 for electrons.
And this number, S, helps us categorize particles into big families. You've got fermions with half-integer spin like 12, 32, and so on.
Those are the matter particles, electrons, protons.
That's right, the building blocks. And they obey the Pauli exclusion principle. Basically, no two identical fermions can be in the exact same quantum state at the same time.
Okay, and the other family?
Bosons. They have integer spin 0, 1, 2. These are typically the force carriers like photons, the particles of light which have spin 1.
And they don't obey the exclusion principle.
Correct. That's why you compile lots of photons into the same state, like in a laser beam.
All right, so spin magnitude is fixed, like S12 for an electron, but what about its direction?
Good question. The orientation, or more accurately, its projection along a chosen axis, is also quantized.
So for our electron, spin 12, what does that mean?
If you decide to measure its spin along, say, the up-down direction, the z-axis, you will only ever find two possible results. We label them spin up or spin down.
Just two options.
Just two, corresponding to quantum numbers plus 12 and Nautica 12 along that axis.
But here's the tricky part, right? Does spin up mean it was already pointing up before we looked?
That's the crucial non-intuitive bit. No, it doesn't. Before you measure, the electron is generally in a superposition of both states, a sort of quantum mixture.
A superposition.
Yeah. The act of measurement itself forces the particle to commit to choose either up or down. We call this wave function collapse.
So the measurement changes things.
Fundamentally. And those labels, up and down, they're always relative to the direction you chose to measure. If you measured side to side instead, you'd get spin left or spin right.
Wow. Okay. So this spin property, it's not just some abstract number. Is it connected to anything more tangible?
Oh, absolutely. Spin is deeply connected to magnetism. A charged particle with spin automatically has an intrinsic magnetic dipole moment.
Meaning it acts like a tiny magnet.
Exactly like a tiny magnet. And this isn't just theory.
You're thinking of the Stern-Gerlach experiment.
Precisely. Back in the 1920s, they shot silver atoms, which have a net magnetic moment because of their electrons, through a non-uniform magnetic field.
And what happened?
Classically, you'd expect the beam to just spread out smoothly. But instead, it split cleanly into two distinct beams.
Two beams, corresponding to spin up and spin down.
You got it. It was direct, stunning proof that this angular momentum property, spin, is quantized. It only takes specific values.
That's amazing. So maybe we can just quickly summarize the difference between everyday angular momentum and this quantum spin.
Good idea. So classical angular momentum, like a spinning planet, comes from motion. Its value can be anything. It's continuous.
Right.
Quantum spin is intrinsic. It's just part of what the particle is. It's quantized fixed values for each particle type.
Like S12 for electrons.
Yep. And maybe the weirdest difference. Rotate a classical object 360 degrees, it's back to normal. But for a spin 12 fermion,
Don't tell me.
you need to rotate it 720 degrees, 2 full turns, to get its quantum state back to exactly where it started.
Okay, that is deeply weird. It really operates under different rules.
Completely different rules, governed by relativistic quantum mechanics, not classical physics.
All right, so we have this weird, intrinsic, quantized property called spin. How does this connect back to entanglement and particles staying correlated over distance?
The connection comes through one of the most fundamental laws in all of physics, the conservation of angular momentum.
We know this classically, right? Like an ice skater pulling her arms and spins faster.
Exactly.
Yeah.
Or a gyroscope staying stable. In a closed system, the total amount of angular momentum never changes. It stays constant.
And this holds in quantum mechanics, too.
Absolutely. But it gets a bit more nuanced. Quantum mechanically, we often distinguish between orbital angular momentum from motion.
But the quantum version of the spinning planet?
Kind of, yeah. And then there's spin angular momentum, the intrinsic thing we just talked about.
Okay.
And then there's the total angular momentum, which is basically the combination of the two.
So here's the kicker, I assume.
Here's the kicker. In a quantum interaction, like a particle decay, the orbital part might change, or the spin part might change. They might not be conserved individually.
Yeah.
But the total angular momentum of the whole isolated system, that is always conserved. No exceptions found, ever.
Wow. That's a powerful statement.
It's bedrock. It stems from the fact that the laws of physics are the same, no matter how you orient your experiment in space, rotational invariance. No other's theorem connects this symmetry directly to conservation of angular momentum.
And this conservation law is what explains entanglement correlation.
It's the absolute physical reason for the perfect correlation, yes. It has to happen this way to obey the law.
Okay, let's walk through it. How does this law create the entanglement? Let's use that standard example. A particle with zero spin, just sitting there, decays into two new particles, say an electron and a positron, both spin 12.
Right, so initially the parent particle is at rest, zero linear momentum. And critically, it has zero total angular momentum, spin 0.
Okay, initial state, zero angular momentum.
Now it decays into our electron and positron. Because of conservation of total angular momentum, the final state, the two-particle system, must also have a total angular momentum of 0.
It has to add up.
It absolutely has to add up. So now think about their spins. Let's measure them along the same axis, say up, down again.
What are the possibilities?
Well, could they both be spin up? That would be plus 12 plus plus 12, which equals plus 1 total spin.
Doesn't work. Started at 0.
Forbidden. Could they both be spin down? Negative 12 plus negative 12 equals negative 1 total spin.
Also forbidden. Still not 0.
So what's left? The only possibility that conserves the initial 0 angular momentum is...
One is spin up, plus 12, and the other is spin down, negative 12, adding up to 0.
Precisely. That's the only allowed outcome. This perfect anti-correlation isn't spooky magic. It's a direct consequence of this fundamental conservation law.
So the particles know they have to be opposite.
It's more like the quantum state they are born into reflects this necessity from the very beginning. They exist in a shared state, described by a single wave function. For the spin case, it's often called the spin singlet state.
And that mathematical description is the entanglement.
Yes. That equation describes a single system where neither particle has a definite spin, up or down, until you measure one. But the state guarantees that whatever you find for one, the other must instantly be the opposite, because they were created as part of this single correlated whole governed by conservation.
They were never truly separate in a quantum sense.
Exactly. Measuring one collapses the entire shared wave function, defining both their properties simultaneously, no matter the distance.
Okay, that covers the spin correlation. But what about the other part? Why do they fly off in opposite directions?
That's explained by a different but equally fundamental conservation law.
Which is...
Conservation of linear momentum.
Right, like pool balls colliding. Total momentum before equals total momentum after.
Perfect analogy. So our original parent particle was at rest, remember?
0 linear momentum initially.
So after it decays into the two daughter particles, the total linear momentum of those two combined must also still be 0.
How does that happen?
The only way is if they have momenta that are equal in magnitude but point in exactly opposite directions. Their momentum vectors have to cancel each other out.
Like recoil from a gun. Bullet goes forward, gun kicks back.
Precisely. The total momentum stays zero. So the electron flies one way, the positron flies the exact opposite way.
So we need both laws working together. Conservation of angular momentum dictates the anti-correlated spins,
Yep.
and conservation of linear momentum dictates the opposite trajectories.
Two independent fundamental laws orchestrating this beautiful correlated dance.
And this isn't just theoretical anymore. You mentioned labs create these pairs. How's that done? SPDC.
Spontaneous parametric down conversion, yeah. SPDC is a cornerstone technique in quantum optics labs.
How does it work, roughly?
Okay, so you take a high-energy photon, usually from a laser, we call it the pump photon. You send it into a special type of crystal.
A nonlinear crystal.
Exactly, something like BBO, beta barium, borate. Inside this crystal, there's a chance the pump photon gets, well, annihilated.
Gone.
Gone. And in its place, two new photons are spontaneously created. These are lower energy, the signal, and idler photons.
So one photon in, two photons out.
That's the essence of it. The nonlinear crystal mediates this conversion. It has a specific optical property that allows it.
And conservation laws must apply here, too.
Absolutely. They're often called phase matching conditions in this context. Energy is conserved. The pump photon's energy equals the sum of the signal and idler energies.
Makes sense.
And momentum is conserved. The pump's momentum vector equals the vector sum of the signal and idler momenta.
So the directions and energies are all linked.
Tightly linked. Experimentalists can actually tune these conditions by adjusting the crystal's temperature or angle, for example, to get the pairs they want.
Incredible control. How do they get entangled pairs out of this? Like entangled in polarization?
Good question. One common way is to use, say, two very thin nonlinear crystals sandwiched together, oriented differently. Maybe one crystal is set up to produce pairs where both photons are horizontally polarized, HH.
Okay.
And the crystal right next to it is set up to produce pairs where both are vertically polarized,
VV.
H or VV.
Right. Now, if a pair comes out, and due to the setup, it's fundamentally impossible to tell which crystal it came from.
Ah, the quantum uncertainty.
Exactly. Then the pair emerges in a superposition of both possibilities. It's in a state that's simultaneously HH and VV.
Which is an entangled state.
Precisely. A common one is HHA plus VHA, properly normalized. This is a Bell state, a maximally entangled state. So STDC is a reliable way to essentially manufacture entanglement on demand. Okay, so we can make them, we can measure them, but this whole idea, this entanglement, it caused quite a stir historically, didn't it? Einstein wasn't a fan.
Not at all. He found it deeply unsettling. In 1935, along with Podolsky and Rosen, he published the famous EPR paradox paper.
What was their main argument?
Their argument wasn't actually that quantum mechanics gave the wrong predictions. They argued it must be incomplete.
Incomplete? How so?
They based their reasoning on two assumptions that seem like common sense. Locality, meaning no influence can travel faster than light, no spooky action at a distance.
Okay, locality.
And realism, the idea that objects have definite properties before you measure them, whether you look or not. Like the moon is there even if nobody's looking.
Seems reasonable.
So their criterion of reality said, if you can predict with certainty the value of a physical quantity without disturbing the system, then that quantity corresponds to an element of physical reality. It must have had that value all along.
And for entangled particles?
For entangled particles, you can predict the spin of particle B by measuring particle A, even if they're far apart. So EPR argued, particle B's spin must have been predetermined from the start.
But quantum mechanics says it wasn't definite until measured.
Exactly. That's the conflict. EPR concluded quantum mechanics was missing something. They suggested there must be underlying local hidden variables, unknown instructions, set at the moment of creation, telling each particle how to behave when measured.
Like sending out a pair of gloves, one's left, one's right, decided at the factory, you just reveal it when you open the box.
That's the perfect analogy for the hidden variable idea. The outcome is predetermined locally.
So for decades, this was just a debate. Philosophy almost.
Pretty much a deep conceptual argument. Until 1964, John Stuart Bell entered the picture.
Bell's theorem. This was huge, right?
Monumental. Bell took the EPR assumptions, locality and realism, local hidden variables, and turned them into a mathematical statement. He showed that if the world worked according to local hidden variables, then the correlations between measurements on entangled particles could only be so strong. They had to obey a certain mathematical limit and inequality.
A Bell inequality.
Yes.
Yeah.
But crucially, Bell also showed that the predictions of standard quantum mechanics under certain specific measurement settings would violate this inequality. They would produce stronger correlations than any local hidden variable theory could allow.
So he turned it from philosophy into something you could actually test in a lab.
Exactly. He provided a clear experimental benchmark. Do the correlations obey Bell's inequality, supporting local realism, or do they violate it, supporting quantum mechanics?
And then came the experiments, a Lane aspect in the early 80s.
Lane Aspect and his team performed a series of brilliant experiments between 1980 and 1982 that really settled the matter for most physicists.
What did they do that was so decisive?
They generated entangled photons using calcium atom cascades and measured their polarizations. They rigorously tested Bell's inequality. Critically, they addressed potential loopholes.
Like the idea that the detectors could somehow communicate.
Right, the locality loophole. Aspect used incredibly fast optical switches to change the polarization measurement settings while the photons were in mid-flight, traveling towards the detectors, which were 12 meters apart.
While they were flying, so there wasn't time for a light speed signal to coordinate the results.
Precisely. The choice of measurement setting on one side was made after the photons had left the source and couldn't possibly influence the other side via any known interaction limited by the speed of light.
And their results.
The results were crystal clear. They found correlations that significantly violated Bell's inequality, matching the predictions of quantum mechanics almost perfectly.
So local hidden variables were ruled out.
The vast majority of physicists concluded that yes, local realism, as envisioned by EPR, is not how the universe works. Nature is spookier than Einstein was comfortable with.
Wow. So just to recap that historical arc, EPR in 35 says QM is incomplete, proposes hidden variables. Bell in 64 provides the test. Aspect in 82 performs the test, and quantum mechanics wins?
That's the essential timeline. It was a profound shift in our understanding of physical reality.
Okay, let's try and pull this all together then. These correlations we see in entangled particles, they aren't some kind of magic.
Not at all. They are direct and necessary outcomes of fundamental conservation laws operating within the framework of quantum mechanics.
So the two main pillars are?
Pillar 1, the perfect anti-correlation of spin, or correlation depending on the state, like one up, one down, that's a direct result of conserving total angular momentum.
Got it.
Pillar 2, the particles flying off in opposite directions, that's a direct result of conserving linear momentum.
Okay. And the big picture implication for reality, because Aspect's results confirmed quantum mechanics.
It means we have to take the quantum description seriously. An entangled pair isn't two separate things that happen to be linked. It really must be considered a single, unified quantum system.
Described by one shared wave function.
Exactly, one non-local wave function, no matter how vast the distance between the components.
And measuring any part of it affects the whole thing instantly.
It collapses the entire wave function, yes. Defining the properties of all parts simultaneously. This action at a distance is real. But, and this is crucial, you cannot use it to send information faster than light.
Why not? It sounds like instantaneous communication.
Because the outcome of any single measurement on one particle is fundamentally random. You can't control whether you get spin up or spin down.
Ah, I see.
You only see the correlation when you and the person measuring the other particle get together later and compare your sequences of random results. The correlation is in the pattern, not in any individual outcome. So causality is safe. No faster than light messaging.
That's a relief. So this journey from EPR's paradox to Aspect's proof, it really shows science working, right? Refining our understanding.
Absolutely. And entanglement, once just a spooky puzzle, is now a foundational concept. It's not just weird, it's a resource.
A resource for new technologies.
Definitely. Things like quantum computing, truly secure quantum cryptography, incredibly sensitive quantum sensors. They all rely on harnessing the unique properties of entanglement. The universe turned out to be far more interconnected and, well, subtle than classical physics ever dreamed.
So maybe a final thought to leave our listeners with. If an entangled pair really does act as one single thing, regardless of distance, does that make us question what we even mean by a separate object at the quantum level?
That's a profound question. It certainly pushes against our classical intuitions about separability and locality.
And if things aren't truly separate in the way we thought, what might that imply about the fundamental nature of space, time, and connection in the universe itself?
That's something physicists and philosophers are still grappling with. It opens up fascinating possibilities and maybe even fundamental limits we don't yet understand.